Okay, sir. So, with your permission, can we start?
Yeah, you can start now. Already it is at 2 minutes past 6. So let's start.
Okay.
Okay, so a very good evening to all respected members in the panel, and a warm welcome to all the participants in this webinar. I welcome you all on behalf of Maulana Abul Kalam Azad University of Technology, West Bengal, India, in the webinar series on application of artificial intelligence on geospatial data. So we have been organizing webinars on a regular and continuous basis on various topics in trend. This is the first in the series on geoinformatics, and it will be our effort to focus on geospatial artificial intelligence, the intersection of geospatial data and artificial intelligence, which is a new frontier of technological innovation, and its applications to solve the intriguing problems of modern times. So today we have participants not only from the state of West Bengal, but also from other states of India and other countries as well. So I would therefore like to give a brief introduction of our university. Our university, Maulana Abul Kalam Azad University of Technology, is a state government technological university and is one of the largest affiliating universities in the state of West Bengal. The university provides degrees in the field of engineering, management, and other professional areas through its 196 plus affiliated institutions and in-house departments. Today, we are privileged to have with us the Honorable Vice Chancellor of our university, Professor Dr. Shoykot Mitra, who has been playing a pivotal role in mentoring and inspiring us to organize these kind of events. In today's webinar, we are really privileged to have with us two very eminent and distinguished researchers and experts who are indeed considered as doyens in the field of remote sensing and geospatial data analysis. We have with us Dr. Suchitra Gopal, professor in the Department of Geography in Boston University, and Dr. Antonio Plaza, professor in the Department of Technology of Computers and Communications, University of Extremadura, Spain. So at the very outset of this webinar, I would like to request our Honorable Vice Chancellor to kindly inaugurate the session with his address.
Okay. Thank you, Dr. Sundatta Chakraborty. Welcome to all the participants of today's very interesting technical seminar. Till now we are having this hangover of using the words seminar, but already you know that we have transformed from the culture of seminar to webinar. This topic is a topic of today already being told: application of artificial intelligence to geospatial data, a pandemic view from the space. I am extremely happy that our head of Department of Information Technology, Dr. Sundatta Chakraborty, could organize it within a very short notice. I can remember that probably a couple of weeks before, I requested her to organize one webinar on geospatial, geoinformatics and geospatial sciences, because this is one of the unique course of our university, and that is jointly done with our government, government of the state, government of West Bengal. So, and I'm very happy to announce that he did it quite successfully, because today we are fortunate to have two very renowned, world famous personalities in this field, Professor Antonio Plaza from Spain and Professor Sucharita Gopalan from Boston. Welcome and thanks to Sir Antonio and Madam Sucharita.
Thank you very much.
Now, at every webinar, being the Vice Chancellor of this university, I would like to tell you that we are having maybe uh, more than 150 courses. And you can imagine it is difficult for me to speak on technical aspects of each and every courses at different webinars. But by virtue of my position, it has become a customary measure for saying something. And whatever I present, that is basically a layman's perspective. Uh, Before when actually many times I feel nervous to say something before the dawns of these different fields. So I would like to speak a few words on this, on the importance of this subject, that not for the experts but for the participants, and those participants who are having this new knowledges or new entrenched in this field. Basically, this is a subset of artificial intelligence which is employed for geospatial application and known as geospatial AI or GeoAI. And that can be called a new front of machine learning that is based on a geographic content. And this geotagged big data, we are talking about big data now, often nowadays, they collected from rich sources like social media stream, satellite imagery from remote sensing, IoT sensors in smart cities for monitoring air, light, sound pollution, personal sensing like connected ambient and wearable sensors that can be presented, that can be processed using this GeoAI for answering many important research and practical questions in a very comprehensive manner. Now this GeoAI technology that can capture and model our environment, linking the place where we live, work, travel, and spend our time to environmental, social, and other types of location-specific exposure to explore their potential roles in influencing our health. So these are the standard applications of these subjects. It can generate new hypotheses, predict disease occurrence, that is very, very relevant now, and help plan and monitor the deployment of effective health promotion and disease prevention and control programs within smart, healthy cities. Besides this population level GeoAI application, there are further opportunities for integration of GeoAI and location-based information intelligence into precision medicine by a well-tailored mobile health intervention targeting individual patient. We are introducing some courses on digital health, and I believe that this particular subject will be of immense importance in making these courses formidable. Now, with the help of simple smartphone application, people can give real-time feedback about the conditions in the surroundings. For example, traffic congestion, the details of it, the peak hours, their experience of it, their rating, whether it is low, whether it is moderate, or whether it is dense. The data is collected, sorted, analyzed, and it enhances its accuracy and precision because of thousands of users contributing to the database. This approach of using geographical location would then not only fill the information void, but it also helps in providing more efficient solutions for particular geographic location. For instance, it would be able to predict which area in the city would face maximum congestion, or which route commuters should take, or whether the vehicle flow can be rerouted. But the applications of GeoAI are in a number of sectors, including those that use location and GIS, ride-sharing companies, logistics, farming, surveying, and infrastructures. These are prominent applications, and these applications are increasing day by day. Ride-sharing companies, Uber, Lyft, in India, Ola, they can take similar feedback from their customers and process the data to find out the density of cars and the availability of drivers. In logistic and supply chain, GeoAI can plug the gap and gather more accurate location information that can streamline product delivery and save time. These are going to be very, very important in the current context. Now, it is now commonplace for a project based on deep learning to simultaneously operate multiple machines in the cloud, each with a large amount of data storage and memory, and all working to tackle the same problem. So collaborative research, this is a reality for these subjects. For a few years, even a few years before, this level of automation and use of deep learning was not considered feasible because cost constraint, limitation of hardware, and implementation of technology. But now it is becoming a reality. This GeoAI capability should be enhanced as it is more widely embraced by the industry, and this is the good sign in business that will substantially improve planning, resource allocation, decision making. I belong to management administration, so this is very interesting feature for me, predicting the surge in demand and supply, identifying the prospects of high and low margin, multiplying supply chain efficiency, optimizing service delivery. So this is the scope is becoming endless. So with this, I again thanks to our distinguished speakers for sparing times to give their deliberation at today's top webinars. And I would be patiently hearing, curiously hearing their deliberation, and I hope that in near future also we would have the chance to interact with them more and more. Thank you.
Thank you very much, sir, for this deliberation. Indeed, this is a significant revolution where this is expanding the use of geographic data in a way that promises to disrupt the entire industry. So sometimes this is called geospatial AI. It is also sometimes called geospatial analytics. It is sometimes called geospatial intelligence, the intersection of geospatial data and artificial intelligence. So this will be critical to all the enterprises and governments ranging from weather centers, defense agencies, healthcare, agriculture, insurance, and so on. So behind the rise of geospatial AI, there are three trends basically. The first is the increased availability of geospatial data from satellites and remote sensing, where over the past 2 decades, there has been a dramatic reduction in satellite launch costs. So at the same time, the emergence of low-cost nanosatellites, satellite constellations, newer sensor technologies, and hyperspectral imaging, they are all creating a growing collection of geospatial big data. And the second trend is the advancement of artificial intelligence, especially machine and deep learning. So we will be hearing about deep learning technologies from Professor Plaza, where he'll be deliberating on the application of deep learning on hyperspectral data. The third trend is the availability of massive computational power. So here comes supercomputing. So widespread adoption of geospatial AI cannot happen without supercomputing systems that provide a massive computing and storage resources required for timely AI-based application development and delivery. So thank you, sir. And so to begin with the deliberation today, I would like to invite Professor Suchitra Gopal to deliberate for her deliberation. So before we begin, I would like to briefly give an introduction of Professor Gopal. She is presently the research professor of Pardee Center for the Study of Longer Range Future since 2010. She is presently the research professor of Boston University Marine Program since 2011. She is presently the professor of the Department of Geography, Boston University, since 2003. Her research is multidisciplinary, dealing with spatial analysis and modeling, GIS data mining, and information visualization, and artificial neural networks. She has applied spatial analysis to address a variety of problems in biology, environmental science, public health, and business. She has also worked on uncertainty issues related to GIS. She has used neural networks for pattern classification, estimation, and mixture modeling. Her current funded research includes the development of a marine integrated decision analysis system for Massachusetts, malaria risk mapping in Ethiopia, analysis of patent activities in China, and mapping health service delivery in Zambia. I would also like to mention that she is a PhD in geography from the University of California at Santa Barbara. She did her MPhil and MSc in geography from Madras University, India. So I would now like to request Professor Gopal to please start a deliberation.
Thank you so much. Let me get my PowerPoint going. Can you see my screen?
Yes, it's visible.
Yes, yes, we can see.
Very good, thank you. So I'm beginning to think more and more about the many different impacts of COVID-19 across the globe. So we have several projects all over the world, and you saw from the introduction, from the very nice introduction, that I'm connected with several departments. I'm a professor in Earth and Environment, which is the name of our department, but I hold positions in biology, in energy and future outlook in terms of the longer range futures, and Center for Remote Sensing. Anyway, so I'm going to take a multidisciplinary perspective to look at what is happening in terms of the COVID-19 pandemic using AI, big data, geoinformatics. This is actually an evolving field because a lot of research is happening right now. And I'm in the midst of writing like multiple grants to many different agencies, looking for many different ways of slicing and dicing our understanding of COVID-19, including work with some physicians at Boston University. So I'm showing you two images, and you all recognize that this is from India, and you can see what happened to the image before, which is shown on the top right corner, and the very clear image of the same place in the bottom left corner of New Delhi. The air quality improved tremendously across the globe, and we can get better data on monitoring even air quality and looking at air pollution in many parts of India pre and post COVID. So in today's lecture, I want to focus on why is this COVID-19 pandemic research, an emerging research agenda in terms of geoinformatics. I want to look at the role of GIS in spatial analysis and what is it that we can do in terms of the data, in terms of analysis, and be a bit more specific. And lastly, to look at the role of big data and AI in this field. And this is again an emerging theme. There's not much work, but I will sort of inform you on things that seem to be interesting in this domain. So if you look at the GIS big data studies, you can see that the role that GIS and spatial data play in the study of COVID-19 is that all data, as I introduced in my title of my talk, can be spatialized. When data is spatialized across countries, regions, states, cities, postal zip codes and so on, it really helps in policy and decision making, and it helps us to understand how to exactly give planning ideas to mayors and governors of the city. I work on a scientific panel both with the governor of Massachusetts as well as the mayor's office on decarbonization and going sort of, carbon neutral by the year 2050 in the state of Massachusetts. So I can tell you that it is very important to look at data in a much more map-like fashion and spatially. The second aspect of GIS and geoinformatics is in the rapid visualization of disease information. Even ordinary citizens want to understand risk, death, and incidence from the point of view of maps. Many people don't understand statistics in terms of distributions and looking at flattening of the curve and so on. They would rather see it on a map in terms of colors. And so visualization has become a key in presenting COVID-19 information to many regions of the world. And we can also spatially track confirmed cases. And as we heard from the introductory talk, cell phone data, drone data, and many things in terms of spatially enabled data streams can allow us to track the data. And people have even tried in Britain, for example, to track this data using cell phone. In the United States and in India, as well as in Europe, there is privacy concerns. Nobody wants to share their data, especially latitude, longitude data of where they are and whether they carry the disease, because they don't want to have that information impact their job or their insurance. So we can talk about privacy issues for spatial tracking of confirmed cases. And of course, the big interest in using AI is predictive capabilities. And we can talk about how to predict, what we know today to the future. In my line of work, I want to sort of look at maps of what is the, where is exactly people following safety rules, regulations in terms of workplaces, and how do we open up the economy, and how can we predict hotspots of emerging disease threats in starting in the month of August or September. We already know that large number of people are congregating on beaches, are congregating in certain stores and so on. How does that impact the disease modeling into the future? I'm working with two professors in the Department of Mathematics who are interested in looking at network models in predicting, and I'd be happy to expand on that idea. The next aspect of the COVID modeling seems to be spatial segmentation. If I know race, age, and prior disease, illness and profiles of people across the US or across India, I can make a prediction on who exactly are the people who are at risk, because in the United States, more than 1/3 of the people who've died are in nursing homes, which means that they are older people above the age of 65 and more. And the people who have died may have had some other underlying health condition like asthma, diabetes, heart disease, and so on. So we could sort of make risk mapping predictions, which are probabilistic, which are based on some kind of base inference, and we can make an exact prediction with certain level of confidence on the spatial segmentation of the population on the ground. We can also manage resources, meaning closure and openings of hospitals, schools, stores, public transport, and so on. As many cities begin to open up, they need to practice social distancing, and everybody needs to wear a mask, as we know. And all these become important as more and more of the economy opens up. And again, we can manage these resources much better if only we know what exactly is the area that they are situated in, and are they in a hotspot. Many economists are also thinking about spatial behavior and decision making. How are people spending money? Such data is available from MasterCard, from Visa and companies like that. And we know that people's spending has gone down quite a lot. Not many people are buying fashion goods or watches or perfumes and stuff. More people are interested in buying things that they use at home. A lot of people are buying tables and computers so they can make their home offices work better. Comes the question, what exactly is the digital connectivity? Even in the United States, I could not talk to some of my students who are in more areas which are more in the rural heartland of the United States, and they had very poor internet connectivity. So even in a very advanced economy, digital connectivity becomes very important, and much of our behavior, whether we want to stay at home and work, whether we want to go around, seems to be pretty much governed by technology. And we could sort of look at that in detail as a determinant in our spatial models. So I do want to look at all the kinds of input data that's coming in to inform us on the study of COVID. So it could be different types of GIS technologies, geospatial technologies, which includes GIS, GPS, remote sensing, drones, Lidar, web mapping, volunteered geographic information, crowdsourced data, applications, social networks, location services. So these are all a lot of words that I'm throwing at you, but I'll try to explain how we can utilize some of these and how people are already utilizing it to talk about COVID mapping. I also want to talk about other enabling technologies like the Internet of Things, a blockchain, and there was a mention of smart city and smart grids. Those come under the rubric of other technologies. So if you look at remote sensing, which is the top left corner, you can see that there's a number of Earth, moving satellites, observational satellites up in the air, including the Sentinel, Landsat, MODIS, and so on, that are observing the Earth's surface, and they are able to sense data, and all of this data can be translated, transformed into making multi-parameter data that can then be used for detecting and analyzing land cover, soil, water, forests, and so on. And the map on the extreme bottom right shows you land degradation in India using remote sensing. So you could sort of look at what exactly can remote sensing do for us in terms of data capture. In terms of COVID mapping, the role of remote sensing is just more observation of changes in terms of traffic, air quality, and people's movement. Probably lots of people in India are moving away from cities to rural areas. And as it was said in the intro, this is a paradigm shift. The COVID is a paradigm shift in much of our thinking. So remote sensing will play an increasing role in observing such data patterns on the Earth's surface. I did want to talk about LiDAR. This is a very powerful technique, and it's very high resolution. It enables us to map three-dimensionally buildings and urban places. And again, this can give us ideas on what exactly is the capacity of these buildings to hold people, what is lit up, what is not, what is the type of energy used in each of the buildings, who is using air conditions, and so on. And such data can also be used for COVID mapping in order to understand, have people really come out of their houses into the workplaces. The global positioning systems, I don't have to tell you anything about it because we all use smartphones. We are using devices as we speak. A lot of people are contributing data, and that is called volunteered GIS information. And there's a lot of crowdsourcing available for bird watching, even for COVID sort of mapping. So people can tell you where exactly are the crowds that they have seen, and you can make some kind of a rating or review based on people's input of data, which is more accurate sometimes. I did want to talk about blockchain. Blockchain is a revolutionary technology that's allowing us to decentralize and distribute all the records. And this is now used in cryptocurrency, and it is also very much will be at play in terms of geospatial informatics. The last aspect is the Internet of Things, where all devices are connected up on the on a platform, and that allows us to share things and sense things, like the idea of smart cities, smart grid, smart energy, and so on. And we all know about the use of drones. This particular drone on the bottom right is showing you the supplies that are being carried during the COVID crisis. Much of the supplies goes to the hospital, so they're relying on drones to carry supplies. But drones, of course, can also capture information, geospatial information on the ground, as well as images of people and movement across the globe. So I did want to talk about visualization of data, of COVID data, very quickly. All of you by now know the GIS maps that ArcGIS has put forth. This is a Johns Hopkins map that shows the data daily, and this is of last night. The number of global deaths at this point is 364, almost 365,000, and more than almost 6 million cases have been confirmed as of last night. The counting over the weekend generally is not very good, but counting over the weekdays is pretty good, and it's reported all across the globe. As you can see, the hotspots have shifted to Latin America. The previous hotspots were North America and Europe. Asia, compared with the population sizes, especially India and China, are not as red as the entire United States at this point, or the entire Europe at this point. And we can wonder why it is so, and discuss that. And you notice that we could make lots of different types of dashboards of the COVID data. And this shows the temporal trends of COVID in India. India is the gray line, and it is showing you that cases have risen. And these are cumulative cases, and they are done on a log basis. And so there's a lot of statistics involved in making these kinds of dashboards. And this particular website that's on top that I'll share with you is has real-time data. We are now talking about flattening the curve. What does that mean? So when you collect the cases and you look at the number of cases on the y-axis and look at time on the x-axis, you can see people who practice social distancing, wear masks, and do protective measures, can flatten this curve and bring it below the gray line much less. So there will be less number of people impacted, less deaths, compared with the extreme left without protective measures, where the peaks are much higher and the hospitals are not able to take in all these patients. And this is happening in many parts of the US as well as in Brazil. They don't know what to do with all the people who are reporting sick to the hospitals. In India, in West Bengal, as of last night, there are 5,000 confirmed cases, meaning there are more people that are yet to be confirmed that may have the virus that we don't know about. And there are 295 deaths directly attributable to COVID-19. And of course, there are many more deaths than this that we don't know about. These are directly under the heading of COVID-19. So this is another website that is also providing instantaneous information on India, and that's reported by Google. So if you look at what exactly can we do with geospatial analytics, we can map, model, monitor all aspects of the disease. We can specifically do what is called clustering and hotspot analysis. I'm sure some of you are already aware of this. This uses Moran's I and G-star statistic and LISA, which is a technique that identifies clustering that's happening in space. So it looks at a spatial distribution of pattern of disease and tells you, statistically speaking, whether there's clustering happening on the ground. There is also, we can use all kinds of risk metrics, risk for the disease, risk in terms of people who are, older. We can do all kinds of cluster segmentation and map population on the ground. using the spatial data analytical techniques. We can also do what is called spatio-temporal analysis, which is called a panel analysis. It's like looking at space and time and making mathematical and econometric models that make predictions into the future. And right now, as we speak, I'm working with colleagues in Vienna, mapping spatio-temporally what's going to happen with COVID. And you can see differences across the many different countries, India, Italy, the US, Spain, and so on. And we can compare their distributions, and based on our understanding of all their flattening of the curve, we can make predictions into the future. We could also do what is called contact tracing, collecting data from the iPhone and do network analysis, which means I can look at your social connectivity on the ground. How many people did you come into contact with, and where are they moving in space? And one person in COVID case, instead of contacting two people and transmitting the virus, could contact, as we know, in South Korea, a person who hopped from bar to bar, spread the virus to more than 300 people within a matter of hours because he went to different pubs and bars. So you could spread the disease rapidly if you have already tested positive. And the last aspect, of course, is predictive analytics, and let's talk about it. The very first thing in terms of satellite data that is fascinating, that's already available from NASA using MODIS instrument, is the aerosol optical depth, which talks about air pollution in India. So the images from 2016 to 2020, taken around the same time between March 31st and April 5th, show you what's happening with the air pollution. Look at the clear image that you get in 2020. There is only air pollution in certain parts of the central part of India, but not in Delhi, not anywhere else, because everything is now blue. And that is an anomaly, because that means you're not seeing the air, aerosol optical depth as you see in the previous images. So this would be a very nice analysis to do, because there are images from satellites looking at it. I am working with a couple of people on this COVID literature mapping. So I do a lot of what is called text mining and looking at who exactly, or what are the articles published in this field in the last 2 years, and what is the connection. So the biggest mention is COVID-19, and the mention is COVID-19 shown in the middle, and each one of these circles represents the amount of citations in the refereed journal literature. And you can see and things like that hurt COVID. And you can see the mention by the US president is also appearing as a blue dot on the extreme right. You can see that there are a lot of emerging topics, including child and children, who are also dying out, because of COVID-19. And social distancing is a very small concept mentioned in literature, but it is more important socially. Articles are written by leading experts in the country, and this would be a very good analysis in terms of what I'm trying to do in the next couple of months. I'm working on it. So here is the social media data, which I told you is very important, because it shows you the number of reports that are coming from people, and this is New York City, who are talking about social distancing, and they're self-reporting. So you can see that the pink areas are reporting higher social distancing. So I can safely say that this is a safe zone. The kind of green areas are the more dangerous parts of New York, and those are not, people are reporting that there's no social distancing in those areas. And this is produced from a source called SafeGraph. And it provides instantaneous information every day on social distancing. So now I want to talk about big data. When we sort of talk about big data, we are talking about the 6 V's, and they're actually more than 6 at this point. But basically, we are talking about volume. The amount of data that we collect every day is humongous. And there is a lot of satellites, and there's a lot of capture of data by phone, by all kinds of media, and that contributes to the volume and makes it big. And so geospatial information at this point is big data. There is also a lot of variety. There is structured data, which is remote sensing data, unstructured data, which is, you know, people's crowdsourced information. There's semi-structured information where information may be missing or lagging, and I can answer questions on that. There is also the velocity and speed at which data is generated. If you have an iPhone and you are collecting data, there is second by second, nanosecond capture of velocity of traffic and social distancing. There is also veracity, which is the trust issue in data. And that's the reason I said nobody wants to report on COVID, because it impinges on privacy. And there's value in all of this data for making decisions, especially on the part of the governors, the presidents, and the prime ministers of different countries. And there's also variability. How can you use this data for other things, interesting things that you haven't thought about before in terms of business? So here is the cloud, of course, on big data. This was done before the COVID days, and it shows you the emerging topics in big data, including fintech, which is the financial aspects of AI. And artificial intelligence, of course, has emerged as one of the most important areas, and it includes pattern recognition, speech recognition, learning and planning, and all of those are big concepts in AI. So if you look at it, we already heard the example of transportation from the Vice Chancellor. He talked about smart cars, and I use it every day for my commute in the pre-COVID days. And that is like, there are many apps that tell you instantaneously what is the traffic. And you can see that you can also answer all kinds of questions in terms of, you know, information, and make maps of it on a country scale or on a city scale. This map on the right is showing you the COVID mapping across the country of China. And here is another map which shows the emergence of novel coronavirus. And this is showing you the spread day by day, collected by all kinds of information and outputs. And you can also make predictions based on these data points using visualization. And here is the one that I told you about in terms of neural network predictions going beyond. And based on the previous hospital admission, based on the disease incidence, based on deaths, you can make a projection into the future, what's going to happen going as far down as October of 2020. So these are the kinds of graphs that many people are using, including my university is using, because we are all planning to reopen in September. And we need to know these kinds of trajectories and predictions, and AI is helping in making these predictions in any particular city or area, you know, looking into the future. Here is another map that is showing you the forecast for the next 5 days on a county by county map of the US. What is the peak hospitalization? What do we know is the incidence? What's the exposure? What's the death? Knowing what we know in the past. AI is very good when you have very good training data. If you have training data on each one of these variables, I can make a prediction into the future, knowing what I know about population and so on. And this is the forecasting and predictive capability of a neural network. So I am going to skip that in the interest of time. And basically, I want to inform you that AI and neural networks have been useful in two ways. One is for exploratory data mining sort of applications and looking at the existing structure and making clustering sort of analysis. And I work on a lot of those sort of applications. The other one is to build models like multiple regression, prediction, and classification. I collect a lot of data from prior days, and I create supervised, training algorithms and make a prediction. Or I can make a prediction on a land cover. What is an urban area? What is the forested area? What is the area that is undergoing deforestation and so on? So these are the two major methods in terms of geoinformatics of using AI. Either you explore your data, try to understand and investigate, or you make predictive models, classification and prediction being important. In contrast, traditional statistical models sort of, don't do a good job because they have an advantage in terms of exactly telling you what is being used in terms of inputs, what are the probabilities, and how did we derive the answers. But the disadvantage is statistical models cannot use a large amount of data, and they don't work well with the noise because they assume all kinds of distributions, heteroscedasticity, and so on. So in contrast, neural networks are many types. They don't need to know the model because it's pretty much like the human brain. They work in noisy environments. They don't need complete data. But their disadvantage in many cases, which is now overcome, is they don't provide you an explanation of how they derived the answer. So if you look at our memories, I let you take a look at the picture, and I always ask people, what did you notice? What is common amongst all these movies? And your brain sort of comes up with an answer immediately. I don't even have to tell you what to think because you probably know the answer better than I do. And I'd love to see what you have to say about this, because our memories are fault tolerant. We can quickly form patterns in our brain. We never ever forget what happened in the past, but at the same time, we are able to remember and incorporate information into our brains. And that's called plasticity of the human brain. So we can think about supervised networks and unsupervised AI algorithms. And recently there's deep learning. And many of you perhaps know the back propagation and models which are used in supervised error-based learning. There is also what is called match-based learning, which is the adaptive resonance theory models. There's also self-organizing and unsupervised model, which are the SOM models. And I'm happy to discuss all of these technologies with you in greater detail. But basically, given the time, I'm moving forward. And this is the human brain with 1,012 neurons and so many synaptic connections. There's no way any computer can replicate the human brain in all its glory. But right now in deep thinking and deep learning, we are distributing the computers, and maybe we will start mimicking human intelligence because we have the computing capability at this point. But still, the computer may, there's so much information that's innate to the human brain. So if you look at the feed-forward models, here is the feed-forward typical architecture, and these are not the deep models. There's a set of inputs. There is the hidden layer, which is the brain, which is made up of the neurons or the processing units, and there's the output layer. And the back propagation algorithm learns by making mistakes. So it self-corrects, sends the signal back, readjusts all the weights in the hidden layer, and keeps training and learning until it produces the best answer. And this is the activation that's happening, and those are the mathematical functions in the feed-forward architecture. And in terms of geoinformatics, we can also look at what exactly is the supervised learning algorithm. And I'm sorry, it's a bit confusing because it's kind of hard to keep at these topics, which are almost take 5 years to learn. And I'm trying to do the best I can with a few slides. So in back propagation algorithm, as I mentioned, there is corrections being made between the actual and the desired response, and the weights are adjusted, and the training happens over and over again. And the questions, of course, are how many input nodes would you use? What is the output in terms of prediction? What are the hidden layers? And what is overtraining, and so on. So there's a lot to sort of say in terms of ANN things. And we can look at, in terms of remote sensing, what do we do? First, we sort of take remote sensing data, which is the input data, and we have an output data which has to predict land cover classes like grasses, conifer, hardwood, and urban. Or in the COVID case, it would be COVID-19, regular flu, other health issues, and so on. And we need to sort of, use this data for training. And we also need to have the, outputs, which is the information that the supervised neural networks need in order to train themselves. So in deep learning, this particular paradigm has shifted because the hidden layers could be multiple hidden layers, because now we have the computing power to make predictions. And I want to show you more of an example of remote sensing. There is a lot of information, and this is kind of the architecture in China. A lot of information, people are being observed. In China, they no longer ask your ID because they already recognize your face. 1,000,004,000 people, 1,000,004,000 are now recognized by face because they are using these deep learning algorithms. Whether it is good or not, they can sort of exactly know what is happening across any given place because they are able to capture all of this, use deep learning, and make predictions. So on the right side, I'm showing you the training scenes, the patches of information that the algorithm uses, and it sort of converts that into crowd counts and density patches, and it produces the maps instantaneously. It's able to make specific, predictions, and it's able to fine tune all its information because it has layers and layers of, layers and layers of hidden units, as I showed you here. So this is a new paradigm in our learning. So I'm going to stop there and take questions, and peace on earth and all the very best to you, and thank you for listening.
Thank you very much, ma'am, for this very elaborate and lucid deliberation. We have lots of questions, but we will take the questions after the session, at the end of the session. I request you to please stay with us. So in the end, after the second deliberation, we will take the questions together. So
thank you.
Yes, so Professor Gopal has very lucidly explained the application of geospatial data for spatial and temporal analytics of COVID-19, hotspot analysis, contact tracing, predictive analytics, etc. She has also discussed how satellite sensors can analyze the changes in air pollution before the lockdown period and after the lockdown period. She has also discussed how social media data can be used to analyze social distancing. She has very elaborately discussed about the use of big data and artificial intelligence in the study of COVID-19, how health map data can be visualized, how neural network applications can be used to forecast about COVID-19 and so on. So thank you very much, ma'am, for this very informative deliberation. I request you to please stay with us till the end of the session. We would now like to move on with the second deliberation. I would like to request Professor Antonio Plaza to please give his lecture. So before we start, I would like to give a brief introduction of Professor Plaza. Dr. Plaza is a full professor with the Department of Technology of Computers and Communications, University of Extremadura, Spain, where he is the head of Hyperspectral Computing Laboratory. He has authored or co-authored more than 600 publications, including 284 journal citation report papers, more than 170 in IEEE journals, 24 international book chapters, and 310 peer-reviewed international conference papers. He is a highly cited researcher. He has been included in the 2018 and 19 highly cited researchers list by the Web of Science and Clarivate Analytics. His main research interests comprise remotely sensed hyperspectral image analysis, signal processing, and efficient implementations of large-scale scientific problems on high-performance computing architectures, including commodity Beowulf clusters, heterogeneous networks of computers and clouds, and specialized computer architectures such as FPGAs or GPUs. I request Professor Plaza to please start his deliberation.
So I'm going to share my screen.
In between, I would like to make an announcement for the participants. After the deliberations are over, we have an online test. The link has been given in the chat box. And there is a discussion forum that has been created. The link has also been given in the chat box. So after the session is over, we would like to continue with the discussion. So I would request all the participants to post their comments in the discussion forum. Yes.
Okay, can you see my screen? Is okay?
Yes, it is visible. Yeah.
Yes.
Thank you very much. Good evening, everyone. I would like to gratefully thank our Vice Chancellor and Dr. Chakraborty, who is a very good collaborator, and we have been working on different topics. I really appreciate this invitation. So I'm going to talk about a more specific topic. I'm going to talk about hyperspectral technology and particularly spectral mixing algorithms. This is a topic that we have been working for several years now. So first I will explain the foundations of this technology, the available algorithms, and then at the end of the talk, I'm going to try to relate how this technology could be used for helping with the current pandemic that the world is experiencing. And I believe there are several ways we can exploit hyperspectral technology, not only from space, but also in situ. So I will talk about this later. First, let me just start by talking a little bit about what is hyperspectral imaging. As you can see in the slide, the idea is we have a sensor instrument, can be in space, can be airborne, can be a drone. But the key aspect is that we have a so-called hyperspectral camera. A hyperspectral camera is able to collect information in multiple bands. For example, if we compare a hyperspectral image with a color image, in a color image, we have only 3 bands, which is red, green, and blue. That means we have a somehow limited amount of information to analyze. But with hyperspectral data, the situation is different because we have hundreds or even thousands of bands, typically comprised in the visible and near infrared part of the spectrum. So as you can see in the figure, if you put together all the information that you have for a single pixel, you no longer have a limited set of values like in a color image or in a multispectral image, but you have hundreds or thousands of values. And if you put together this information, you have a detailed spectral signature that gives you a very clear and very specific information about the object that you are observing. Of course, hyperspectral data are big data because we have multiple bands, the spatial resolution can also be high, and generally we need high performance computing infrastructure to process this data, especially if we want to do real-time analysis. So normally we use GPUs or clusters or this kind of HPC platforms. Now, as I mentioned before, there are different platforms from which we can collect hyperspectral data. Traditionally, satellites have been used to provide global coverage, which is great in terms, for example, of covering large areas and also to have a certain temporal resolution in the sense that the satellite will provide some revisit time, and we can collect information on the same area at multiple days. But somehow the temporal resolution is also limited. So there are other possibilities like airborne platforms. For example, with an airplane, we can have a hyperspectral flight a la carte. That means that we can have the flight on a particular area of our interest, and we can increase the spatial resolution because we can control the altitude of the flight. And now recently we have also drones or UAVs, which is a very emergent platform and has a lot of advantages. We have more control because we can have even better spatial resolution, but we still have some power energy constraints. So there are three kind of platforms, and in my opinion, these platforms are all complementary. Depending on the phenomena that you want to observe, you can use either of those or even combine the information coming from all of them. For example, let me show you a very interesting experiment. This is a UAV that has on board a hyperspectral camera and a GPU. This would allow you to collect hyperspectral data in real time, control the spatial resolution, and even perform the analysis in real time on the fly. So what are the real advantages of using hyperspectral imaging? We have this paper published in Science many years ago by Alex Getz, 1985. And already in this paper, Alex Getz already foresee the main advantages of the technology. For example, we identify the biochemical composition of materials. We can also get detailed information about the composition of the observed spectral signatures, but we need to deal with a problem that is the mixing effect. That means the spatial resolution may not be enough to fully characterize different materials. And this is particularly sensitive when we are observing something that is very small, something like a bacteria, something like a microorganism. So we need to deal with this mixing phenomenon. And there have been many algorithms proposed to deal with the mixing problem in hyperspectral data. Here in this slide, you can see the problem of mixed pixels when you have a hyperspectral data cube, like the example that you can see in the figure. It might be the case that you have a pure pixel, for example, in the case of water. In this case, we are talking about homogeneous and macroscopically pure material. But in other cases, you can have mixed pixels, for example, soil and rocks, vegetation plus soil, or even intimate mixtures that happen at the microscopic level. So how to deal with this problem? In the end, exploiting hyperspectral data is closely related to how accurately we can deal with this mixed pixel phenomenon. In the literature, we have two main approaches. One is the linear model, and another one is the nonlinear model. Of course, the linear model that you can see in the plot on the left is very simple. You basically assume that the different materials in the plot, material 1, material 2, material 3, interact linearly with the incident radiation, in this case coming from the sun. And then the response that is measured at the imaging instrument, at the hyperspectral camera, Y, is a linear combination of the materials that we are observing, weighted by their proportion inside the pixel, the fractional coverage of the pixel. This is what we call the abundance of the material. Of course, we can imagine that in the real world, everything is not so simple. We very rarely have the materials segregated as separate patches. So we can have situations like the figure in the middle, in which trees will create different kind of nonlinear mixing effects. And even if we think about intimate mixtures, it is difficult to predict how is the behavior of these mixtures, because we would need to have some information a priori about the materials, particularly about the nonlinear function. And it is very difficult to have information about such nonlinear function in advance. So that's why the linear model has been dominant in the literature, although there's still a lot of work to do towards new models for nonlinear and mixing. Now, if we focus on the linear mixture model, it is simple and it's geometrically easy to understand. The goal is to find a set of macroscopically pure spectral components. Let's say that we view the hyperspectral image projected in two bands. Okay, if instead of thinking of hundreds or thousands of bands, let's project the hyperspectral image into a two-dimensional space. So what we try to look here is the pixels that can help me understand other pixels in terms of linear combinations. For example, in a color image, these pixels, these pure pixels would be very clear because there are three basic colors, red, green, and blue, that can be used to interpret all the other pixels in the data as combinations or mixtures of these three basic colors. So in this case, if we look at this two-band representation, we would have exactly the same idea. We have three pure components. This would be the end members. And these end members define a triangle that includes all the other pixels in the data. For example, if we think about yellow color, yellow is a mixture of red and green. If we think about a mixture of red and blue, we have magenta. So it's kind of the same idea. If we want to understand how much of a certain end member is present in a given pixel, we just need to have the basic end members, the basic pure components. And then we can mix the image by saying, okay, this pixel is 50% water, 30% vegetation, and 20% soil. That is the way we can look at the fractional coverage or abundance of each end member in each mixed pixel of the scene. So using this very simple geometrical interpretation, we can create a more general and mixing framework that you can see in this slide. Of course, there is some pre-processing steps that we need to do with the image. There is some atmospheric interference that we need to reduce. Optionally, we can do dimensionality reduction to bring the data to a lower dimensional space in order to simplify computing. Step, we have several techniques that I'm going to describe later. And the goal of the mixing will be to have two main combination of pixels. And essentially the idea is to grow the volume. For example, let's say that I take one pixel and I replace by another one and calculate the resulting volume. This volume is bigger than the previous one. So this pixel is more likely to be an end member. If I do that with all pixels and all possible end member combinations, in the end, I can reach the simplex with maximum volume. And the points that define this simplex are the so-called end members, because they can be used to encompass all the other pixels in the data. This algorithm is quite easy to implement because it's basically a raw force algorithm, in the sense that we just need to try all possible combinations in order to get the highest volume. Remember that this only works if we have pure pixels in the data. That means we need high spatial resolution to calculate these end members. Another limitation of this algorithm is that the spatial resolution is not included. That means that we are only working with the spectral information in the data. But let me give you a very simple example. Let's take an urban hyperspectral data set collected over an urban area, and let's randomly shuffle all the pixel coordinates of the individual pixels in the data. If we apply the mFinder algorithm, we are going to have the same output results. And this is somehow unreasonable because we are discarding the very rich spatial information that we have in the data. For example, we have a river, we have urban area, we have streets. Somehow we would associate these easily recognizable spatial shapes to spectrally pure end members. For example, a water end member, an urban end member. So there are algorithms that include the spatial information, and I will show you later how these algorithms can improve not only the end members, but also the fractional abundances. And there is yet another problem of these algorithms, is the fact that sometimes, as mentioned before, the image may not have any pure signature at all. For example, in satellite data, we have very limited spatial resolution. So what to do in this case? As you can see in the figure on the left, the data distribution in blue, the points in the data may actually give us hints about where the location of the end members could be, but we don't have the true end members in the data itself. So there is a whole family of algorithms that do not assume the presence of pure pixels in the data. And we have several strategies like minimum volume based algorithms. Basically, the idea in this case is not to find the simplest with maximum volume, but to find the minimum simplex volume that includes all the data in the hyperspectral data set. This is because the main problem these algorithms have is that maybe if we don't assume the presence of the n numbers in the data, we can have unrealistic signatures. And that means that we are not having signatures that are related to real materials that we have on Earth. So this is also a very important problem that we will see later, that it can be solved by using spectral libraries. That means that we go to the field, we collect spectral signatures from real materials in the field, and then we use these libraries to find the n-numbers in the data, even if the data doesn't contain any pure pixels at all. Okay, so I'm going to show you some experiments, and in mixing is very popular, very typical to use synthetic data because it's very difficult to obtain ground truth information about n members and fractional abundances. But synthetic data, the properties of the algorithms to control the signal to noise ratio, to control for instance, the complexity of the mixtures. So we can do a lot of experiments in order to validate our algorithms. In our case, we use a very simple set of synthetic data. And let me show you how we build the data. We start with fractal images because they provide some spatial correlation, some realistic spatial information. And then we perform some k-means clustering. This is basic clustering to obtain a set of clusters. Now for each cluster, we select some library spectral signatures. For example, there is a very well-known spectral library provided by the US Geological Survey, and we have mineral signatures that we can mix to the different clusters that we have. Normally what we do is to simulate realistic scenarios. For example, the abundance normally is not constant inside each region, but we can have, for instance, a pure signature at the region center, and then we have the signature purity decrease linearly away from the center until we have a mixture data. Different algorithms, the synthetic images with different signal to noise ratios. Infinite means we have no noise at all, and then the ratio can be varied. Normally, hyperspectral sensors provide very high signal to noise ratios. So the closest situation is that we go to the rightmost part of the column. Now here we have two groups of algorithms. The algorithms on the bottom, MBC-NMF, MBEAS, MBSA, and CSAL, these are all algorithms in the minimum volume family. This means that they do not assume the presence of pure pixels in the data, while MFinder, OSP, and VCA assume the presence of pure pixels in the data. So you can see that for very noisy scenarios, most algorithms without the pure pixel assumption cannot derive good n members. And minimum volume techniques are also quite sensitive to noise. So we don't have a good scenario for either class of algorithms. But as soon as the noise is reduced, the performance of the two families of algorithms, with and without the pure pixel assumption, becomes very similar and becomes more balanced. So in optimal conditions, you can see that the algorithms without the pure pixel assumption perform slightly better because they are able to cope with the outliers and with the noise that we have in the data. Let me also show you some results with real data. This is a very popular hyperspectral data set that has been imaged by Averis, which is the NASA JPL instrument. It's a very well-known instrument, and the data site has been imaged since 1995. So we have extensive information for this data set, including the materials that are present in the area, also the fractional abundance. And what we have done is to calculate the error, the per pixel error provided by different algorithms. So what you can see in the picture, when you see blue, it means that we have very small error. When you see red, that means that we have very high error. How this error has been calculated? We have simply reconstructed the original image using the end members and the fractional abundances estimated by the different algorithms. That means that we use the linear model in order to reconstruct the original image, and then we calculate the error with the original image. So in this case, we can see which parts of the image are more critical or more difficult to reconstruct. As you can notice, all these 3 columns that we have in the bottom use spatial preprocessing using different techniques. So in general terms, you can see that spatial preprocessing, for example, this region-based preprocessing or spatial spectral preprocessing, is able to provide very good maps, very good reconstruction errors, no matter what algorithm we use. No matter we use MFinder, OSP, BCA, which are pure pixel-based algorithms, or MBSA and CSAR, which are non-pure pixel-based algorithms. So in general terms, we can conclude that spatial information helps. As far as you can use spatial information, that is good for our mixing purposes. Now let's move on and talk about the problem of what happens if we don't really have pure pixels in the data. As I mentioned before, there is also a possibility to use libraries. Spectral libraries have been available for a long time, and we have libraries for minerals, for vegetation, for man-made objects. So the idea that we propose in this paper is to use the library to perform the unmixing. The library normally contains a large number of spectral signatures, so it's a combinatorial problem. But the advantage is that we no longer need to find the end members in the image, because ideally we have the end members in the library. And also we don't need to estimate the number of end members that we have in the image, which is also a very difficult problem because, as I mentioned before, maybe there are no pure pixels in the data. So it's very difficult to estimate the number of end members when we don't have any pure pixel. So the formulation you can see is very simple. We have Y is the hyperspectral image. Then we have a linear interpretation of the image, which is based on the combination of A, which is a full spectral library, out of which we only use a few columns, because typically for each pixel, we normally have a limited number of end members. We don't have 100 end members for one pixel. We have maybe 4, 5, that is the typical number. So we can select 4 or 5 end members from the library and then estimate the fractional abundances that are codified or encoded in the matrix X. You can see the matrix X should only have a few active lines. That means that only a few active end members are present in the data. The dimensionality of the image Y is N, where N is the number of pixels, L is the number of bands, and then the abundance matrix is given by X, where we have M values multiplied by N, which is the number of observations. So M ideally is the number of signatures that we have in the library, that is quite high. So in order to solve this problem, basically we minimize the reconstruction error, as you can see here. We minimize the reconstruction of the original observation, Y, using the multiplication of A times X, which is the library times the abundance fraction. And we impose an additional constraint, that is to minimize the number of fractional abundances that are different from 0, because we are assuming that the number of spectral signatures participating in the mixture is very low. So with this sparse mixing, we can also include spatial information, and that's very simple because we just need to include another term in the optimization problem. This term, in this case, is the total variation, which basically enforces smooth abundance transitions between members that are spatially close. If we have one pixel made up of water, it is very likely that the next pixel will also have some water. So that is what we include in the solution of the problem, to have a kind of better description of the abundances. And you can see in this simulated image, we have the ground truth here on the left. We have the sparse and mixing solution. And here at the right, we have the sparse plus total variation. You can see that the abundance estimation is better with the total variation because we take into account the spatial information. So this is basically the same thing we already observed with the other classic n-member algorithms, in which including the spatial information is highly beneficial. So I'm going to show you also some results for the copyright data. You can see for these 3 different minerals, we are going to focus, for example, in this chalcedony mineral, we have the ground truth obtained by USGS in the tricorder algorithm. We have the result of the linear unmixing. We have the result of the SANSAL, which is the traditional sparse unmixing. And then we have the sparse plus the total variation, SAL-SAL-TV. You can see that the abundance of this chalcedony mineral can be better delineated, can be better described than in the original linear mixing or SANSAL. It's more similar to the ground truth. So we again have a benefit from spatial information. And then we can also use other tricks like collaborative sparse mixing. As I mentioned before, ideally we have only a few active n members in the library. So this situation that you can see in the figure with a lot of spurious contributions from different n members should be avoided. So instead we can apply another term in the optimization problem to have something like this. As you can notice, we go from a lot of noise in the matrix of fractional abundances to more straight lines, meaning that we are making more clear the contribution of the different n members. So this is an even better solution. And of course, as you add new terms to the optimization problem, the complexity of the algorithm gets higher and you need more and more computational power in order to solve the problem. So let's finalize with a summary. In order to do hyperspectral unmixing, a very important question is, do you have a spectral library available in advance? If you have a spectral library, this is a huge advantage because we have a whole family of sparse unmixing algorithms using total variation, using collaborativity, using groups. So this is a very powerful way to solve the unmixing problem. But sometimes we don't have a library. So a main question to ask is, do we have pure signatures in the hyperspectral image? This might be difficult, and it might be the case, because we can have a high spatial resolution hyperspectral data, for example, collected with a drone or with an a la carte flight. So in this case, it's important to have spatial preprocessing because we have seen in many examples that this helps the overall processing and characterization of the unmixing problem. If we don't have pure signatures in the data, it is going to be very difficult to estimate the number of n members. This is going to be a main challenge. If we happen to know in advance, because we have some ground truth or some a priori knowledge, the recommendation is to use minimum volume algorithms. Even if we don't have, we can use the concept of collaborativity that I mentioned before to try to estimate the number of n members by minimizing the number of rows in the abundance estimation matrix. But still is a difficult problem. So we have some threats, not only this, but also the fact that maybe the mixtures will be nonlinear. So far, we have only dealt with linear algorithms. So the linear model may not hold, and in this case, we need to do something else. So a very active line of research is to train a deep learning model in order to be able to learn the nonlinear function. Although it's difficult, it can be done directly from the data. So in our case, we have developed a deep autoencoder for a mixing that basically tries to address this problem. And this has been a collaboration with Dr. Chakraborty. It was published in the Transactions on Geoscience and Remote Sensing last year. And as you can see, this autoencoder has 2 parts. One part is intended to remove outliers. It's a set of stacked autoencoders. And this is because we have observed that outliers, noise, are very harmful to estimate n members because an n member can be completely misunderstood by an outlier. If we have noise, this is exactly the definition of an n member. It's something that is different and is extreme. So we need to remove these outliers in order to have a very good estimation of the number of n members and also the n member signature. So we perform first this outlier removal, and then we use a variational autoencoder to perform the actual unmixing. And we enforce 2 constraints, non-negativity and sum to 1. This is in order to avoid estimations that fall outside the simplex, because in this case, the abundance would be negative, and this would have a a very unrealistic physical interpretation. So we try to have signatures that can enclose all the pixels in the data. Let me show you some experiments that we have collected with a hyperspectral image acquired over the Henry Island of the Sundarban Biosphere Reserve of West Bengal in India. The data were provided by Dr. Chakraborty, and as you can see, it consists of 137 times 187 pixels and 155 bands with 30-meter spatial resolution, which is not bad for hyperspectral. Now, what we did in this experiment, in this paper, was to estimate the end-member signatures of different species. And in particular, we analyzed sensitivity of our algorithm in comparison to other traditional algorithms to the presence of outliers and noise, because this Hyperion data set has some strong noise. So as you can see in the graphical representation, we show the first principal component versus the second principal component. And our algorithm provides end members that are closer to the actual data estimates than other algorithms that are very sensitive to outliers. In this case, the outliers are marked in a red cross. So we can see that our algorithm generally discards well the outliers before finding the end member signatures. And since we have some ground truth, we can also plot the end member signatures obtained by our algorithm in red with the ground truth reference signatures in blue. And you can see there is a lot of spectral similarities. So we can conclude that the deep learning algorithm is doing a good job in this particular case. Now let me conclude the talk by talking a little bit about hyperspectral microscopy applications. So far, we are looking at things from space or from drones or from airborne devices, but we can also use a hyperspectral microscope. And in this case, we combine a hyperspectral camera with a microscope and provide high spectral resolution and unity amplification for microscopic cells. That means that spectral data can be collected on the cell scale. And the microscope that we are using in this research has 5 types of objective amplifying lenses with different magnitudes and a built-in transmitted light illuminator acting as the light source. So that means that we can perform tissue analysis or even observe microscopic objects. And what we have been trying to do is try to see if we can contribute to the detection of the COVID-19 using this kind of hyperspectral technology. Now, this is a collaboration with Professor Jun Lee at the School of Geography and Planning in Sun Yat-sen University. And here you have her contact details in case you have detailed questions, but I'm going to talk a little bit about what we are trying to do. So as you can see in the figure, we can use COVID-19 samples. We are working with different hospitals in China to provide samples of the virus. It is still not completely feasible to see pure spectral signatures of the virus because of the spectral resolution of the microscopic system, but it's very, very close to pure sample. So our goal is to create a spectral library of COVID-19 pure spectra, and also to include mixtures in the library. We are considering mixtures with different materials like glass, fiber, water, plastic. So our idea is to be able to have a very comprehensive, very detailed spectral library of the COVID-19. Once we have the library, it will be feasible, we believe, to analyze the spectral signatures in detail and understand what are the sensitive bands. For example, what are the spectral absorption characteristics of the virus, even when it is mixed with different materials at different concentrations. And in this particular role of detection, spectral unmixing will be very, very important because we strongly believe that with this detailed spectral library and the suite of sparse unmixing algorithms that we currently have, we can perform detection of the virus at different concentrations. For example, here we have simulated data in which we have 40% plus 60%. That means the virus in this case has concentration of 40%, and this is mixed with the surface in 60%. Now the goal would be, of course, to perform some kind of in situ detection, real-time detection on public places. For example, identifying which areas should be cleaned, which areas should be disinfected, or where could be remains of traces of the virus. We are currently working, as I mentioned, with different hospitals, but we are looking at this initial idea, and hopefully we can have some additional results. As you can see, the email and the website of Professor Lee is in the slide, so we can point you to her in case you would like to have additional questions or information about this. Okay, so I'm going to conclude the talk by giving some key ideas. Hyperspectral data offers a very important source of information for Earth observation. Now it is available. We have hyperspectral camera in satellites, airplanes, and drones. There are many uses of hyperspectral technology, not only in Earth observation, but also in medical, industrial applications, and so on. And at the end of the talk, we have discussed the use of hyperspectral technology to detect the presence of microorganisms in different surfaces. This is feasible, for example, in water, wood, plastic, fiber, glass, and also at different concentration levels. That means that we don't really need to have a very pure spectral signature of the microorganism, because we can use some mixing to detect the presence of the virus even at very low abundance. Let's say even 10%, we could be able to detect the presence of the virus. We also aim at building very detailed spectral libraries to monitor the presence of this substance, the mixtures with other materials, the relevant bands, the spectral profile, so that we can understand more about the spectral characteristics. And in the future, we plan to continue exploring additional applications of hyperspectral imaging technology to other important societal problems. Okay, so this is the end of my talk, and I'm very happy if you would like to ask some questions. Thank you very much.
Thank you. Thank you very much, Professor Plaza, for this very informative lecture on spectral unmixing of hyperspectral data. You discussed about spectral unmixing, linear and non-linear, basically for subpixel mapping. You have also discussed end-member detection algorithms such as nFinder and amongst others for pure pixel detection. You also discussed about the comparison of different end-member algorithms using synthetic data and real data. You also discussed about the application of deep autoencoder for unmixing and hyperspectral microscopy applications. Thank you very much for this very elaborative and informative session. Now we have lots of questions for Professor Sucharita Gopala as well as Professor Plaza. What we have done is we have selected a few. We have selected a few questions because it will be very difficult to answer each and every one. So first of all, I would like to take up the questions for Professor Gopal. Ma'am, are you there?
Yes.
Yes.
I'm here.
So the first question is, can spatial analytics be done by unsupervised algorithms for better prediction?
So, you can do unsupervised, more in a sort of an exploratory fashion. And the thing for detection would be you don't have any supervised data. What are you looking for? You don't have an answer. So the unsupervised method is used to investigate and explore. So I could be looking at it in order to form a hypothesis. I can't just sort of use it for prediction because it is just for investigation, exploration, and generating hypotheses. Like even in the world of the hyperspectral mixing and unmixing that was talked about just now, I could use all the spectral data, run an unsupervised network on it and try to figure out what are the nonlinear clusters, and what exactly is the feature set that's going in to explain that cluster. And can I sort of get an understanding out of it as an expert and know that this is speaking about COVID and this is speaking about non-COVID surfaces. It generates hypotheses and questions. It cannot be used to predict.
Yes. The next question.
Because I don't know what I'm trying to predict, right? I don't know what the answer is that I'm trying to predict. So.
Exactly. The next question. How could geospatial data identify a person having a disease?
That is a tough one. The person either has to self-report, right, which is very difficult, but there is the app in the United Kingdom that is doing that. And both, Apple and Google have gotten together so people can self-report. But I doubt that that'll work. Self-reporting is pretty low. But hospitals can have a more private kind of thing, which is Mass General in Boston is doing it. Their patients, their people who have reported to be at risk, they can track them. And that's a very private network. I don't think that information will be shared by with the public. So you either have to self-report in order to monitor yourself with crowdsourced data, or you have to have a hospital or a healthcare network that does it privately. I don't think that such data should be shared publicly because of privacy concerns. I could get sued in the US.
Yeah. Another question. How blockchain can be implemented in geospatial domain?
How locked in? What is
blockchain? Blockchain can be
blockchain. Oh, yeah. Blockchain. All of these technologies provide the dispersed sort of network, and these are all sort of emerging technologies with the smart city, smart grid, and IoT that I talked about. And you can see that blockchain implementation, especially of financial sort of information, is proving to be very useful in order to understand how people's spending patterns and so on. So blockchain's utility in terms of information is the dispersed sort of network and obtaining information from the fintech companies, the financial technology companies. So it's an emerging technology. IoT is more widely used for smart grid and smart city applications.
Yes. Now, what are the career opportunities of geospatial AI?
So this is sort of emerging even as we speak, because companies like Google and Facebook and Microsoft too have a lot of interest in AI. And so does the company ESRI that is participating in all this COVID activities. So these are emerging sort of, industries and companies utilizing AI, especially with geospatial data. Everybody wants to fly a drone. Everybody wants to deliver things remotely. And we are beginning to understand how things have to be implemented, using, geospatial and AI in combination. The good example that was mentioned is traffic. Traffic patterns and traffic things are very widely studied. I would like to sort of also think about, wider applications. How do we decarbonize? How do we sort of move forward in this post-COVID world? These are emerging applications. In terms of job opportunities, people mainly look for things like deforestation. I'm working on a very large project of China's Belt Road Initiative. How is China's Belt Road Initiative impacting biodiversity? How did we get into this world of COVID? Because we are cutting more and more trees, we are coming into contact with more and more wild animals. Can I make a prediction of population density and biodiversity coming together? Those are all AI applications. So it's pretty much in the realm of research, but many companies and the Chinese banks and World Bank and people like that want to understand risk. You can also think of risk in insurance. The insurance companies will be using geospatial risk widely because they want to model the world in terms of climate change. What's the future? And that's AI.
The last question, how to deal with the personal privacy issues and the need of real-time data for network-based models. Do you think this will make the Internet of Everything move faster?
So this is a question again to do with data privacy, and it's kind of a difficult one to answer. People should kind of opt in to say that they're sharing their data. And I don't know how many people want to reveal their health or their whereabouts, right? Nobody wants to share that data knowingly. And of course, nobody reads these documents and they're signing automatically that they'll share everything. I think this is going to be a big concern. Maybe, like I said, hospitals, schools, universities may ask the students to sort of sign in so they can track you because they have a vested interest in your well-being. But I don't think it will be shared publicly on a wider basis. I don't think that that's possible.
Okay,
Something has to change and people are not willing to change.
Okay, thank you, ma'am. We have some more questions for Professor Plaza. The first one, what is a spectral regression?
Oh, spectral regression. I read some papers about spectral regression. If I'm not confused, it's a technique for manifold learning. It's related with the understanding the data cube, the distribution of the data. So in the context of spectral unmixing, it is useful for estimating the subspace in which hyperspectral data live. For example, we have a full hyperspectral data cube, but there are some correlations, some redundancies between the bands. So effectively, the data lives in a subspace, and spectral regression tries to find this lower dimensional subspace, which essentially provides the dimensionality, the reduced dimensionality of the data, and indirectly we can use it to learn the number of N members. So it has been used both to reduce dimensionality and also to estimate the number of N members, which is a difficult problem, as I mentioned in my presentation.
Another question on unmixing. What is the exact function of intimate mixture for doing unmixing?
That's a very good question. The problem is the exact function is different for different materials. For example, if you try to unmix vegetation, is different from water or is different from minerals. You don't always have linear function. So that's what makes nonlinear unmixing so difficult. Even if you are using vegetation, different kind of trees, different kind of leaf models can lead you to a different nonlinear unmixing function. So that's why so far people have focused on linear unmixing because it's simple, it's geometrically easy to understand. You can understand the idea, you can implement it. And we all know that when we use linear unmixing, we are making some errors. This is unavoidable because we are making a rough simplification of the real world. So in order to solve this, you have two ways. One is if you have some a priori information, if you happen to know the nonlinear function because you are expert in vegetation and you have an idea about how the nonlinear function can be, then you can use this nonlinear function included into the unmixing. The other way is to try to guess or try to estimate the nonlinear function. You can try to do this with deep learning, but you need some training data. And we are again in the need of some library or some a priori information. That's why I strongly believe that using libraries of spectral signatures is the future, because somehow you avoid looking for pure pixels in the data, you avoid this need for a priori information, and dealing with nonlinearity is always a big issue. But this is a very interesting question. It's exactly the key problem of nonlinear unmixing, how to estimate the nonlinear function.
Another question, which time series data is best to use?
Sorry, can you repeat the question? I didn't.
Which time series data is best to use?
Which time series?
Time series data. Time series satellite data.
Talking about multi-temporal data. I think, in my opinion, there is Yeah, I think in my opinion, the best time series is a combination of different satellite data, because relying on one single satellite may not be enough. So if you really want to go multi-temporal, I believe one satellite may not be enough. We have, for example, in Europe, we have the Sentinels. They provide relatively good coverage. The spectral resolution is not that large. There is a full hyperspectral instrument to be operational very soon. But the good thing is right now we have different sources of information. We have satellite data, we have airborne, we have drones, we have cameras, we can collect in situ data. So if we want to really go multi-temporal, I think we can exploit different sources of data. And multimodality is a very important research topic nowadays. And I also believe not only hyperspectral data is needed. We can have a high spatial resolution, high spectral resolution, even social media data can be combined. So we have so many different sources of data that I believe today it makes no sense to use only one. But of course you can do that. You can use the Sentinel in the European Space Agency, and there are other sources of publicly available data. But my advice would be to look into multimodal data. As Professor Gopal mentioned in her presentation, there are other kinds of instruments like Lidar and synthetic aperture radar, not only optical. So today the advantage is that with this big remote sensing data, we can include many different kinds of data and take advantage of multitemporality, because different instruments provide different temporal acquisition. I don't know if this answers the question. But...
Yes. Another question, someone has asked, how do I classify microorganisms in a soil?
How do I classify microorganisms in a soil? I think, well, classification, I didn't talk about classification because I focus more on spectral and mixing, but I mean, it really depends on if you have a priori information or not. If you want to do supervised classification, in this case, you have some training samples. Then you train, for example, a neural network, and then in the testing phase, you can show new samples to the network and see if you were able to learn or not. Unsupervised classification is more challenging, because we know in this kind of problems, it's difficult to do classification if you don't have some kind of a priori information. But you know, as I mentioned in my presentation, we have hyperspectral microscopy data, so we can do a very fine spectral resolution, and also we can have some labeled information in advance. So there are plenty of deep learning classifiers, very robust, very accurate, and I believe the classification problem can be applied in many difficult scenarios, including the one the attendee mentioned in his or her question.
The last
So
question.
I would like to add a little bit there. You know, there was the question of multi-sensor sort of classification and multi-temporal realms. And you could sort of use what are called semi-supervised neural networks, which can sort of take empty fields for which you have no idea about, and you can have a different paradigm. Of course, it will take you a long time to sort of figure all this out, but you could do it. There are other algorithms that are available to mix and match. The other problem that we frequently run into when we look at multiple sensors for classification, and we've done a lot of work using MODIS at 1 kilometer resolution, Sentinel and Landsat at a much finer resolution. That kind of question also takes some time to set up, and you really need to have like perfect training samples where the classification ontology, what are you going to classify forest that is available at a MODIS scale? What happens to it at the Sentinel Landsat scale? What would you call it? And do you have training samples for all of these kinds of mixtures that occur at a much different, pixel resolution? So all of these are very interesting questions. Takes a long time to set up, will keep you busy, but you could do it if you have very good training samples.
I fully agree.
Yes, so the last question, in case of remote sensing, validation with ground data is very difficult. So what is your suggestion to make it better or easier?
This is for me.
Yes.
Go ahead.
Anyone can answer. This is a very general question.
Yeah, it's a difficult one. I'm not sure if Professor Gopal has an answer because.
So I am going to answer because I'm working in the field in 3 different locations which require that kind of expertise. The first example that I want to give you is Lake Victoria. We are looking at the floating vegetation, mangrove vegetation that you talked about in Lake Victoria. This is an invasive species that is changing the ecology of the Lake Victoria, and more than 5 million people live around the lake and fish in that lake. And the fish is all changing. So I'm using genomics and those kinds of things with a student, looking at what can I learn about the ecological structure of the marine organisms and how does it inform me about the changing floating vegetation. From the point of view of remote sensing, I have the images of the lake at various points and I really can't detect, you know, what is happening. I have images, cloud-free images, only on certain days. I'm using a 30-year time series to look at this lake and understand what exactly is happening to floating vegetation, because it is not stagnant, it is moving. The vegetation is moving over different time periods. And some years I have no data because they were cloud contaminated. So this is a challenging problem. There I want to use other types of data, including people's observation on the ground. And the people's observation on the ground on the lake is what are called transects. You know, ocean remote sensing is a challenging topic. And I'm working on 2 ocean projects where we have transects taken on certain days and certain times. And somehow I have to use that data with the remote sensing data to validate. So there is a lot of science and expertise that goes into answering whether I could use that data and whether that could be validation enough, you know, in terms of fully getting the ground truth. Ground truth data with Curtis Woodcock in California has been also challenging. We observe forests, we observe woods and land cover in different parts. We don't have enough experts who can run around and collect the data, so we are doing drone sort of technology to fly the drones and understand what exactly is the expertise. The third type of ground truthing we are doing is using aerial photos and high resolution imagery, even using Google Earth and Google Photos to get to map things. And I've done this kind of mapping for Zambia. Looking at their road network, nothing is available as an official road network for Zambia. And I'm trying to understand the journey undertaken by pregnant women seeking hospital, services and medical services. And we are just mapping it by hand using crowdsourced data and open street maps. So there are all kinds of validation possible. Use the expert, use surveys and transects if they're available at certain parts of the year or certain times of the year, or use high resolution imagery and use an expert to assess the imagery.
Thank you very much. We have lots of questions, but due to lack of time, we will not be able to address each one of them. We have a discussion forum where the link has been given to the participants. So we can take this discussion forward. So you can ask your questions in the discussion forum and our experts can answer them. So our Honorable Vice Chancellor is here with us. Would you like to say anything, sir, regarding the session?
All these lectures, that was nicely deliberated. I think all the participants, they got immensely benefited. And as Professor Chakraborty was telling, it is quite natural. There will be lots of questions, but we have limited time. But to make these interactions, the sustainable, we have created that discussion forum or discussion prompt. There you can put your questions and query. And it's a wonderful experience to all of us. We must agree to listen to Professor Sucharita Gopalan and Professor Antonio. Thank you very much for responding to our call and presenting your expertise and experiences, sharing your ideas. We would like to see you again and again. Then you have only increased our expectation, and in near future, we are all of our students, while they are being confined at home, they would be immensely benefited from your deliberation. That I strongly believe. Thank you once again.
Thank you, Professor. It's a great honor.
Thank you. It's a pleasure.
Thank you very much, sir. So this webinar is the first of its series, as I had mentioned initially. So I would request you to remain connected with us and participate next Saturday also. We have Professor V.K. Mohan with us next Saturday, and he will be deliberating. And on 6th June and on 13th June, we have Professor Raul Fetosa. He will also be deliberating with us. And so we will be sending you the links, and I would request both of you to remain connected with us. And I would like to thank both of you on behalf of the university to have spared time from your busy schedule. And thank you very much for this excellent deliberation. And we hope that we will see you once again. And I also request you to kindly answer the queries that our participants have after they post their queries in our discussion forum. So I will personally email the link to you. It has also been given in the chat box. It is there. So thank you, Professor Plaza and Professor Gopal, for being here with us and for sharing your expertise with us. So thank you very much.
Thank you.
Thank you so much. Thank you.
Thank you.
Bye-bye.
Bye.
And for the participants, there is a short quiz that you have to undertake. And after answering the test, you will get the certificates. So it will take some time. Maybe after 1 or 2 hours, you will get the certificate. So the link for the test has been given in the chat box. And just after the session ends, please be with us and give the test. Okay. The link, I request the host to please give the link. So I request the participants to please click onto the link. You will get a time of half an hour to answer the questions.
These links can be taken as a screenshot and can be kept with them.
Yes, you can take a screenshot. The participants can take a screenshot and give the test so that we can log out of the session.
Should I close the screen sharing now?
The screen sharing, I hope everyone has copied the link. It was there in the chat box. Yes, please let them know how they will get their certificates.
Yes, ma'am. After completing the quiz, we will upload the certificate after 1.5 or 2 hours. The quiz link will be active for 30 minutes. After that, the assessment process, and we will then upload the certificates.
Where will the certificates be uploaded?
Certificate link has also been displayed, ma'am.
Yes. One of the participants is asking to post the certificate link at the chat box. It is already there, I think.
Yes, in the screen sharing it is displaying, ma'am.
Not only in the screen share, it is there in the chat box as well. The certificate link is also given. Like the participants are asking, please give the certificate link. It is available. All right. So I think they have all of the links.
Yes, ma'am.
Professor Plaza, he is still with us. Sir, are you there?
Yes, I'm here. Yes, Sandata, I'm here.
Yes, so shall we log out? Maybe we can discuss about...
Yes. I will go to the forum now, and I will interact with the participants there.
Right. Yes, yes. So do you have the link of the forum with you?
Yes, I think I already...
MAKAUT blog.
Yeah.
Is MAKAUT blog
MAKAUT blog.
Blogspot.
Okay. Yes, so I will be there. Thank you so much for organizing this seminar. It was really a pleasure.
Pleasure here too, and I wish June Lee, she had also come. Maybe next time.
Yeah, I will try to convince her. I will convince her to participate in future editions, because she's very busy now with the proposal application. She told me she's very sorry she cannot be with us today, but I'm sure in the future she will be happy to participate. Okay. Thank you so much. And I will be here next Saturday. I will follow the seminar.
Yes, I will send you the link for the next session by mail. and then accordingly you can.
Very good idea.
Yes, actually there is some problem in the network, I think. I'm not able to clear.
Okay, I hope we can.
Yes.
Ma'am, should I close the session?
Yes, sir. So we are closing the session.
Okay. Okay.
Yes.
Take care.
Okay.
Thank you very
Thank
much.
you. Yes. Okay. The host, please close the session.
Yes, ma'am.